All right. I hope everyone can hear me. It is 2 minutes past the hour, so I think that's plenty of time uh, for people to join in. People are still joining in. I want to welcome everyone and thank you. Thank you so much for being here. I hope you'll find this free webinar informative and helpful. Um, I will start just as a bit of a logistics here. I'll introduce myself and Verist Engineering so that if you don't know who we are or what we do, you're going to have an opportunity through this free webinar to get to know us. And then, not without spending way too much time there, we're going to proceed with the main topic of today's discussion, which is modeling soft actuators and devices. So, again, thank you all for being here. Uh, I'll start with introducing myself. I'm Nick Vasios. I'm a lead engineer here at Verist Engineering. I have been with Verist since 2020, following the conclusion of my PhD at Harvard University in material science and mechanical engineering. My PhD work was on the computational mechanics for the design, actuation, and control of soft robots, and I worked under the supervision of Professor Cardia Bertoldi. I got my diploma in mechanical engineering before that from the University of Thessaly in Greece, where I'm from, and I was also one of the first recipients of the Abacus Structural Analysis Associate certification by Dassault. Um, Now, this is enough about me. It varies as a whole. We combine multi-physics simulation with multidisciplinary subject matter expertise to drive innovation across industries such as medtech, pharma, healthcare, energy manufacturing, chemical processing, as well as many others. Example areas of our work include nonlinear solid mechanics, material testing and modeling, fluid mechanics and turbulence, multiphysics modeling, heat transfer, and failure analysis. We take an hierarchical approach to problem solving, employing an array of tools with varying levels of sophistication. Most of the projects that we work on start with ideation, hand drawings, dimensional analysis, and scaling arguments, so that we can identify key physical mechanisms and pinpoint critical parts of the device or the process that guide performance. We can then move on as necessary to develop computational models, answering questions such as what scale of model is suitable to solve the problem? Do we have good geometry and material properties? What are the important outcomes? And finally, and that's perhaps the most important, we communicate the findings into clear, actionable, and science-backed advice to stakeholders of various backgrounds. Concerning solid mechanics specifically, and particularly solid mechanics modeling, which is also my area of expertise, we deal with problems that involve nonlinear materials, large deformations, contact, adhesion, debonding, impact loading, coupled physics, and many, many more. Um, we also perform in-house testing in our test lab to validate our finite element simulations and models, but also to measure material properties of complex materials. Finally, we also perform material model calibration, where we select appropriate material models and calibrate their parameters to our test data, which we're then using in our finite element models. Um, Now, that out of the way, that is a brief introduction of who I am and who we are as Verist Engineering and what we do. We're now in a position to start our webinar on modeling soft actuators and devices. I want to say this, throughout this webinar, you don't have to wait till the end. If you have a question that you would like answered, drop it in the Q&A. When the webinar is over, I will go to the Q&A and try to answer as many of the questions that you have as I can. So you can go there at any time and ask the questions. I will address them. I will address them at the end. So to begin, over here, it is probably fair to say that perhaps the first thing that comes to mind when thinking about robotics in general is something like this. Maybe a little bit old-fashioned to say in 2026, but this is a factory production line from Kia Motors factory. Robotic arms, rigid links, performing orchestrated sequence of action with very high precision. As you can see from this video, interaction with humans is nowhere to be found for safety reasons. This assembly line is separated from the rest of the factory. In complete contrast, this is, in case you're not familiar, this is what came to Disney's mind when thinking about soft robotics, squishy, inflatable, very resilient assistant, meant to be a personal nurse and guardian. Uh, Seamless plug here. Incredible movie, by the way. You should watch it if you haven't. Beyond science fiction, however, soft actuators and devices have been making strides in the real world as well. Uh, Shown by a few examples here from the last decade, from surgical applications, biomimetics, locomotion. Soft actuators can provide unique solutions to problems where traditional rigid robots are not great candidates. They can definitely do things that the rigid counterparts are not able to. Um, at a glance, soft actuators and devices are all distinctly different from one another. They all have different shapes, comprised of different materials. They are controlled using different mediums. Some are inflatable, light activated, piezoelectric, chemically activated. Um, and the relationship between the required input stimulus for each one of these and many more um, um, is often quite nonlinear. This is something quite unique to soft actuators and devices. So I would like us to discuss this first. Um, Now, nonlinearities, which is what usually, and we'll talk about this, entangles the relationship between input and output or stimuli and response, can come from several different sources. Here, since we're talking about soft actuators and devices, we're going to mainly mention four of them. First, we will begin with the material. Um, so, um, most the nonlinearities, and I should mention this first. The nonlinearities here are essentially what entangles and what complicates the relationship between input and output. So the difficulty here is that unraveling the relationship between the input stimulus and device functionality is almost impossible through just doing experiments alone when we operate in such a nonlinear space. Because of that need to somehow more intelligently and quickly um, unravel this relationship and quickly determine what is the output for a given input, we are in need for computational modeling, something that will greatly simplify the process of predicting the response of a soft actuator or device. So beginning with the material, um, most soft devices consist of one or many polymer materials, the behavior of which is very rarely linear. Polymers exhibit nonlinear elasticity, hysteresis, temperature dependence, and many more features um, that make the behavior appealing for several applications, but simultaneously challenging to describe, capture, and predict. Um, um, so here, and this is something that we do a lot of at Verist Engineering. Uh, we we are in need to be able to understand the response of polymer materials and to be able to accurately describe it. We need well-designed experiments that allow us to determine the key material properties, such as small strain modulus, strain limit or onset of failure, time-dependent behavior such as viscoelasticity or viscoplasticity, temperature dependence, sometimes all of the above. And we need all of those to be able to plug into material models that accurately represent the observed material behavior in our finite element models. here to the right, we're showing a DIC of a tension test from our drop tower. These are tests that we do almost every day here at Varus, testing different polymer materials to be able to measure, quantify, and model the polymer response, the response of different polymers. However, we should not adopt a binary approach to material model complexity. In the sense that if we go from simulating, for example, a silicon rubber using an isotropic linear elastic model, it doesn't mean we will end up with a better model necessarily if we conduct every single possible experiment and calibrate a super complex material model that involves all of the dependencies, temperature dependency, rate dependency. We need to be able to identify what key elements of the material model behavior are important for our application, conduct a corresponding test to calibrate the most appropriate material model for what we're trying to do. Now, this, as you can probably understand, this can be very challenging and requires a lot of experience to get right. What kind of complexity is the necessary amount of complexity? We are fortunately a world recognized expert in this area because we do this so often and we've been doing this for so long. So I encourage you, if you have any material modeling or testing questions related to your applications, uh, two things. Look out for our free and paid classes and webinars on material testing and material modeling, specifically of polymers. And if you have a specific application that you would like help with uh, determining the behavior of your polymer or of your material, reach out to us. We'll be happy to assist. Um, so material, as we said in the beginning, one source of nonlinearity. The next one we're going to talk about is symmetry. Now, the concept of a symmetric solution is not just appealing when we're dealing with analytic approximations to solid mechanics problems, but also in our finite element models. It's very convenient and very nice when we can get away with a symmetric model. After all, a finite element model that takes advantage of symmetry can be dramatically more efficient, use considerably fewer resources than a model with no symmetry at all. However, a frequent phenomenon in problems involving large deformations, and soft actuators and soft device problems are often involving very large deformations. A frequent phenomenon is the breakdown of symmetry. For example, and here we're showing just an example that we're going to talk about in a little bit more detail in a few slides here. Um, the inversion of a spherical cap. We have a spherical cap that looks perfectly axisymmetric. The problem starts as axisymmetric, but can suddenly, after finite deformation, adopt non-axisymmetric modes of deformation. And what does that mean? If we model the problem as axisymmetric to start because we see an axisymmetric domain and we're thinking, oh, I'll just model this as axisymmetric. It is probably the smartest way to go about this. It's going to be so much faster. The problem there is that an axisymmetric model is limited to only predicting axisymmetric solutions. This might be profound to many of you. Of course, you have an axisymmetric model, you will always be predicting axisymmetric solutions. However, if we do that and the non-axisymmetric response is something that actually happens in our problem, um, then we will be predicting a response that is not reality. Now that conversely, in the other end of the spectrum, if we do not include any symmetry and we have a fully 3D simulation, then we are also running into problems because in a problem like this with the inversion of the hemispherical cap, the problem still possesses cyclical symmetry. So if you don't have any sort of symmetry in your problem, you might not have a convergent solution because of that cyclical symmetry. Somehow you need to help the solution enough so that you can get a convergent result, but also include the freedom in your model to express what solutions are possible and to obviously choose the one that requires the least amount of energy there. So That's another thing that requires some experience to get right. So the advice here is to include um, only the necessary amount of symmetry. And some trial and error obviously helps there if you have the capability to run experiments um, in conjunction with your finite element models. It will greatly help identifying what matters and what doesn't, um, and what kind of symmetry you need to account for. So to get to the bottom of this, for the hemispherical cap, for example, half symmetry is the right amount of symmetry. Half symmetry meaning we have the 3D dome and we'll cut it in half. So we're modeling half of the 3D dome. This way, we are predicting solutions that are converging. We are getting rid of the cyclical symmetry, kind of like conundrum, and we are getting a response that is very well representing what is actually happening during the inversion of the spherical cap, as you saw in the previous slide by the comparison of what our model predicts and what is happening in reality. One more thing that can be a source of kind of like um, not nonlinearity here, but a kind of like a good practice, so to speak, when we're modeling soft actuators and devices, uh, concerning steady state versus transient solvers or steady state versus transient solutions. Um, I think engineers are generally in tune to kind of like search for static solutions in most of the problems, unless we're dealing with a heavily dynamic scenario. This is not necessarily a bad place to start. Static solutions, however, might not always represent the real behavior of a soft actuator or device. Now, this is exemplified if the nonlinearities the function of the actuator relies upon manifest in the form of one or multiple instabilities. So it's very common to have a scenario like the one shown in the figure here to the right. You have a pressure volume response, you have a peak, you have a local maximum, and then say you're controlling your actuator using pressure, you have an instability, you have a snap through instability that in reality it manifests itself with a dynamic response. Um, so the convergence of a static solver does provide some comfort in trusting the nonlinear relationships governing the behavior of such actuators. However, in the presence of instability, static solutions often do not represent reality. Again, one example might be the inversion of the hemispherical cap, for example, that as we saw from the previous example, when we invert that hemispherical cap, we have a sudden release of energy that makes those rubber domes jump. Um, so in such cases, a dynamic solver might be more appropriate. Um, and the reason is that the elastic energy stored in the actuator or device prior to the instability can often be rapidly released in the case of a snap through or snapback instability and converted into kinetic energy. Such a conversion is not even allowed. It's fundamentally prohibited in a static solver. Everything has to be in perfect static equilibrium. There is not even the possibility for kinetic energy in the system. Additionally, some extremely complex problems can benefit from an explicit integration scheme that some of you might be already familiar with. Um, while a very powerful tool, explicit integration schemes, explicit solvers should be used with a lot of caution when their predictions are not backed by experimental observations, since their convergence is not guaranteed. They're predicting a solution, but you don't know if that solution is actual reality or if it's just garbage being integrated over and over, like through time. So using explicit solvers to compute the solution of fundamentally static problems is typically computationally inefficient. So in this case, again, we have to be smart about identifying what kind of problem we're dealing with, selecting the appropriate tools for its solution. Um, there is very rarely a one size fits all solution. You have to adapt in depending on what you are working with. Um, I want to go through a couple of examples where we see kind of like the sources of nonlinearities. We see some of the best practices that we talked about regarding how we model the material, the choice of symmetry, and the choice of solver, for example, and showcasing what we can do. And maybe you find some similarity there in some of your applications. Maybe you draw some inspiration for something you would like to model yourselves. I hope you'll find them. I hope you'll find them useful. So we begin with one example that we already talked about, answering essentially the question of how a pop-up rubber toy jumps. Um, you might have played with one of those. Um, in this case study, what we were trying to understand through experiments and also finite element modeling is um, what is the essentially the mechanical behavior behind this jump. Even further, we want to be able to predict the jumping height as a function of geometry and material properties. You can imagine a situation where, of course, this being a case study, it's not dramatically interesting, but if you develop a well like a well you have a well developed accurate model for something like this, you can tune your parameters, such as what the material how the material behaves, or how the geometry changes, and you can see immediately how that affects jumping height, if your model has that predictive ability. Now, these toys typically consist of a silicone rubber, and they have the shape of a hemispherical cap. The way this works is like you manually invert inside out. So you introduce a lot of deformation in the form of elastic energy stored into the system. Now you place this on a flat surface, and due to friction and other mechanisms, after a few seconds, typically, all of this energy will suddenly be released, and the toy will jump, and it will make also a loud popping sound, which fascinates kids. Um, Here, in this slide, we're showing an animation of the inversion of the hemispherical cap using a simulation that we developed, and also in the right-hand side, the strain induced by the material during this inversion. Now, we go from zero in the strain energy space, which is the stable state, obviously the undeformed state, to another kind of like stable state at a very large displacement, which is the inverted state. However, that state is metastable because with the slightest perturbation about this state, and we can see it from the analysis, we will immediately release all of the elastic energy we have stored and revert back to the initial energy state, snapping back to its initial shape, and that's what causes the toy to jump. Now, doing a simulation allows you to be very quantitative about how much energy exactly you're storing and how quick is the transition from the metastable state to the initial state, and whether there are other states that could be stable in the process. And this, as you can see, is an analysis that uses 3D simulation that uses half symmetry. It has you know the right amount of symmetry here to be able to fully predict the path of deformation from one state to the other. Um, in this case, our finite element model utilized all three best practices that we talked about. Um, we used the finite element model with just the right amount of complexity. The material model behavior was just simply nonlinear elasticity. We perform a test in our lab to measure the response of our silicone up to moderate strains, and we calibrated a hyperelastic model to that behavior. So that's what we used in our material model. We used half symmetry to allow for the slightly non-axisymmetric inversion of the snap and the snapback of the cap. And we use the dynamic solver, since the inversion of the cap and the jumping is a dynamic process. Um, and as you can see in the image to the right, we are able to predict not only the temporal response with great accuracy of the jumping, but also compared to experiments. You can dive into the case study for more details that's posted on our website. We were able to very, very accurately predict the jumping height. So um, best practices that went into that. In this next example, this is the example of a soft robotic gripper. Another example that we have posted as a case study on our website that I would like to talk to you about here. Um, the gripper that I haven't shown you yet, I'll show you in the next slide, consists of four identical fluidic bending actuators like the one you're seeing here, that like the one you see in the animation. Now, these actuators have a fluidic cavity that you can see in the cross-section view to the right, um, that we can inflate. And when we inflate that, those little segments, those little chambers inflate, contact each other, and because of the stiffer layer shown in orange here at the bottom, the actuator bends. Now, this emulates the motion of a finger, so these actuators naturally could be arranged in any kind of sequence to form a gripper and grab objects. Um, what I would like, however, to talk about here is that um, is the nonlinearity in the pressure volume relationship, which is essentially the input and output of our system. Either way you think about it, for example, if you're controlling pressure, you have a change in volume. If you have a change in volume, you're modifying the internal pressure of the system. There is an inherent nonlinearity there that manifests in terms of curvature of the system, but we're looking in the pressure volume space, which is the state diagram for our actuator, and there is a nonlinearity there. Now, somebody naively could perform a very simple experiment, measure the initial stiffness, and assume the system will behave linearly. Um, and we would be terribly wrong if we did that, because I just pick here one example. The blue curve is the actual response of the system, and even though it might not seem like that, the gray dashed line is a linearized response about the base stiffness in the beginning. It looks like the stiffness is wrong here at the beginning, but if you zoom in all the way to zero, this is kind of like the stiffness that you're getting. It might not end up being like a terribly bad prediction for super, super high volumes. The curves do meet up again, but that's just coincidental. I want to draw your attention what happens at 75% normalized volume change. Um, you would be predicting with a linearized approximation about 98 kPa for the internal pressure of the actuator, where the actual, or sorry, 95, where the actual internal pressure is 48. So this is almost 100% error. It's 98% error. Definitely not an error we would be comfortable with. Uh, so in this situation, it's important to model the material and the response of it uh, in our analysis appropriately to be able to capture this nonlinear response, to know that it exists, so that we can actually use this with the right amount of pressure or put in the right amount of volume. Um, and this is the final product after we have developed a finite element model of the one actuator on its own to determine its response. We have the capability to develop a finite element model of four of these things that are now. This model obviously takes advantage no symmetry, because we wanted to lift an actual object and to see the model's capability in holding on to that object in various conditions. We started shaking the object to see when the object will lift off. Um, but the important thing here is that with a model like this, you can very quickly iterate on what happens if the material is stiffer, what happens if I inflate the actuators, which are my gripper fingers in this case, with a higher amount of pressure. How much pressure do I need to hold on different objects or different stiffnesses or different weight and different frequencies when I'm shaking the object, and things like that. Things that are typically more time consuming and require more effort to be answered in a laboratory setting. Having a model like this is incredibly powerful. Um, now, Finally, I have one final example here. There's not so much in the nonlinearity here from the behavior or the modeling perspective, but there is the niche of the multiphysics interplay here between electrostatics and mechanical or fluidic actuation. So here we have what we call a piezoelectrically enhanced self-artificial muscle. So you have a sort of artificial muscle. All this is like, in this case, it's a cylinder that has some piezo strips. Those piezo strips, because they're significantly stiffer than the elastomeric base that is shown in blue, uh, when we mechanically actuate this, when we pressure drive this and we increase the internal pressure, those piezo strips don't want to elongate at all. So what happens is the actuator kind of like balloons, like the contraction of a muscle, and it contracts exactly like a muscle would. So when we supply pressure to the system, it expands and reduces in length. So if there was something attached to this actuator, it would lift up. If there was a weight, we would lift that weight. Uh, However, there's another, because of that piezo strip, there's another way we can achieve the same kind of thing. Instead of applying pressure to the system, we can apply voltage to the piezo strips. Now, because of that voltage that we apply, we introduce an electric field, and those piezo strips will shrink in length. They would still have like a balloon type of deformation, not as excessive, not as distortive as the pressure driven case, but we will also achieve the same idea of kind of like reducing the length of our actuator. Uh, this space that can be like the space of actuation that can be driven either using electrostatics or pressure is really complex to navigate with experiments alone again, and it's surprisingly easy to navigate with a multiphysics simulation. This one we did in COMSOL multiphysics. Um, so this is why I chose to talk about this here. So one thing that one can do when you develop a model is first determine the response in the actuation, each actuation type on its own. The voltage driven type, which is drawn in this figure on the left with the green curve, and the pressure driven actuation, so with absence of voltage, so no voltage on the right. So you can see that we can essentially achieve the same amount of Z displacement contraction with both. The response obviously is much different. It's much more linear in the voltage space. It's more nonlinear in the pressure space. Uh, Having though that capability to have two mechanisms that are independent from one another that allow you to interface with your actuator is really powerful. It can enable a lot of very interesting things that a simulation can very easily predict. And then you can go hopefully and in a lab setting or in reality to verify that those work indeed. A few of them I've chosen to show you here where we have what we call combined actuation. So we have pressure on top of the electric field. So in this top one here, we're pre-inflating the pressure at a given level, ranging from 13 kPa for this blue curve all the way to 51 at the top for this yellow curve. So that sets the base state for the actuator. And then on top of that, we add an oscillating voltage, kind of like a alternating signal that allows us to have some oscillation about this base state. So this amount of control is possible because we have two ways of interfacing with the actuator. Um, and a much more complicated one here at the bottom where both the voltage and the pressure are varying with time. And we are plotting the displacement and the pressure profile. The displacement, I think, is what is mostly interesting for an actuator like this. Um, is you know oscillating and taking different values over time. You can also think about cases where you would optimize this uh, to something that you would like the actuator to be doing. Again, something that can fairly straightforwardly be done with a finite element model, but not so easy to tackle just doing running experiments on an actuator like this alone. So with that, I want to kind of like recap and say that when we're dealing with modeling soft actuators and soft devices, there are a lot of sources of nonlinearities. The four that are most, in my opinion, most prominent to soft actuators and devices are material nonlinearities, so nonlinearities in the material response, geometric nonlinearities, so the geometry of the actuator might be nonlinear or complex, that introduced nonlinearities in the sense that it's not a straightforward kind of like straight beam bending kind of thing. Um, we have nonlinearities introduced due to large deformation. So we saw that in the case of snap through or snapback instabilities. Um, in nonlinearities essentially present at large deformations due to those large deformations. And finally, actuation. Actuation on its own can be a source of nonlinearity depending on what medium you use to actuate your device, whether that's air, whether that's electrostatic or magnetic field, or a combination of those things. You can have an additional source of nonlinearity there. All these things said, because nonlinearities are simultaneously what makes soft actuators and devices appealing, but it's also what makes the response so hard to predict with great accuracy. And this is, in my opinion, why we need good models. And we can, at I personally and we at Veris can help you with those if you're in need of developing one or need assistance with material modeling or testing. Um, so this covers everything that I would like to talk about from a soft actuators and soft devices um, aspect for today's webinar. Um, I want to put on your radar that we are hosting free webinars twice a month, so biweekly in a biweekly cadence. So I urge you, if you're enjoying these and you're finding them useful, go on our website under free webinars and you can see the upcoming ones, the ones scheduled for, there's one scheduled for April 22nd, hosted by my colleague Joe Barakat on CFD modeling for mRNA vaccine production. There might be others also that might be of interest to you or some of your colleagues. These are free to join. They're 1 hour or less. So if you see something interesting, I urge you to sign up. And we always happy to connect with you, meet you, and answer any questions that you might have, and can help in any way that we can. So with that, I want to thank everyone that attended today's webinar. Thank you for your time. I really appreciate it and your attention. I hope you enjoyed the content that I was able to share with you today. Here's my contact info in case you would like to reach out to me personally. I'll be happy to talk to you at this point. If you have any questions, there's something posted in the Q&A section, or you would like to send your question directly to me, I'd like to take 10 or 15 minutes or the remainder of this hour to answer any questions that you might have specific to um, soft devices or soft actuators. Thank you. So I'm launching the Q&A session, putting your questions as you have those. I'm reading them as they come in. Um, have you considered dissipative mechanisms, rate-dependent hysteresis in my soft actuators? Yes, I have. In none of the cases that I've shown today was there like there wasn't any hysteresis or rate dependency in the models there, but this is something that um, I can talk to it with great detail, but I can say that we're doing this almost every week, because the behavior of polymer materials, and specifically for how they're used for soft actuators and devices, is very rarely not dependent on the rate of deformation or hysteresis, for example. So we have the capability of not just measuring how we can quantify this rate dependency or that hysteresis of the material, but also how to calibrate a model that greatly predicts this and put this in our simulation. The difficulty there is in determining how much rate dependency there is and how you put it into a finite element model. Once you do that, the model can be identical, essentially. You don't need to change much. It's just the material card. So yes, I have considered dissipative mechanisms. They do matter in certain instances. It just so happened that in none of the cases that we talked about here, there wasn't one. So thank you for the question. All right, let's see if other people have questions. All right. If nobody else has any question, we can wrap up this webinar. I would like to personally thank you again for joining, for making the time, for attending this webinar. I hope you enjoyed it. I hope you learned something or it spiked your curiosity to go try something new. We'll always be happy to talk to you and answer any questions you might have. So thank you.